Hello, everyone, and welcome to Dana-Farber's Department of Data Sciences Frontiers in Biostatistics webinar. Before I turn it over to our organizers and speaker today, I'd like to point out a few items. The webinar today will be recorded and will be available on our YouTube channel within the next week. You can find our channel at youtube.com/DFCI Data Science. If you have a question for the speaker or the organizers, please use the Q&A tab. Our faculty organizers will manage the Q&A session before and during the talk. With that, I will turn it over to Svetlana for our speaker introduction.
Thank you very much, Erica, and thanks everyone for joining. Today, our speaker is Dr. Duan. She joined the Department of Biostatistics at Harvard School of Public Health last summer. She graduated in 2020 from University of Pennsylvania. And she's interested on statistical and computational methods for integrating evidence from different data sources, identifying signals from high dimensional data, as well as accounting for real world data, meaning that suboptimal data, the missing data, as well as measurement errors. And today she will tell us about the integrative learning methods for electronic health records and other medically related data. So Dr. Duan, please.
Okay, thank you for the introduction. Let me share my screen. Okay, great. I will get started. So hello, everyone. First, I wanted to thank you for inviting me here. And I'm very glad today to have this opportunity to share with you some of my recent work. Actually, before I moved to Boston, I was very excited and expecting to have a lot of interactions with colleagues around the Boston area. But unfortunately, we were all locked down for a whole year. But I still, I'm very looking forward to meeting with all of you in the near future. So today I'm going to talk about a few projects related to distributed statistical learning and inference. And this line of research is motivated from my past experience working with collaborators from research networks and what they call the learning systems. So for example, the patient-centered Outcome Research Institute, PCORI, has sponsored this efforts of PCORNet, which is a network of research networks. So it involves 9 large clinical research networks and 2 health plan research networks, and also a coordinating center. So every logo here you see stands for either a clinical research network or a health plan research networks that involve data from multiple institutions. And among them, I have been collaborating with PSNet, which is a pediatric learning system involving 8 children's hospitals, and also one Florida that is a clinical research network that incorporates around 12 hospitals at the state of Florida and covers over 40% of their population there. So in addition to these, that's within the states, and there's some other ones. So for example, this consortium called 4CE stands for the word for C, which is a consortium for clinical characterization of COVID-19 using EHR data. So as you can see, 4 stands for 4 continents. You see data from their sites from North America and Europe and South America and Asia. And this effort is led by the I2B2 International Academics User Group. And I2B2 is a clinical platform that's led by Dr. Zach Cohen at Harvard Medical School. So they provided actually a lot of useful and scalable tools to better extract information from these clinical data sets. And so there's another one that's sort of from a worldwide perspective. So this is called the Observational Health Data Sciences and Informatics, known as the ODAC. And ODAC is a global research community that also provide this platform for researchers who have observational data. They can join in and they can discuss some questions of common interest. And as you can see, Odyssey now has contributors from over 20 different countries across the world, and they have over 100 databases that cover around 500 million patient records. So, and a lot of efforts within this community has also been focusing on like creating tools for doing like data harmonization. So converting different data sets, even with different language, so into a unified format, so that really like can enable different data sets to be able to talk to each other. So so this is about Odyssey, and they have a special focus on evaluating drug safety and drug efficacy. And since they already built this large platform and has different types of infrastructure, so this type of research community can react relatively fast to some like public health emergencies like COVID-19. So their group has already been focusing on a lot of different works focusing on COVID-19 studies. So as you can see, there's a lot of, so about moving from the clinical side to genomic research, there's also many different biobanks, and a lot of efforts has been devoted to try to extract information from different type of these biobanks in order to identify novel genes or make genetic risk predictions. So more and more efforts has been developed in order to facilitate multi-center studies. And one obvious reason for this is that multi-center study can provide a larger sample size compared to a single site study, which can lead to more generalizable findings, greater statistical power, and most importantly, the ability to study some rare conditions that cannot be usually studied using data from a single site. And in addition to this, it also brings together investigators who share and leverage resources, expertise, and ideas. And therefore, the quality of the study is often improved through this team science. And on the other hand, however, in addition to the problem I just mentioned about data harmonization, which of course is a very challenging issue, there's also other challenges. For example, there's data privacy issues. And that means like the patient level information is prohibited often from sharing across different institutions due to rules and different policies about privacy issues. And especially when it involves data from multiple countries, it's really hard to share data. And even if it's de-identified data, then we can try to manage to share the de-identified data across institutions. It often involves long waiting time and a lot of communication costs, and that will cost like manpower, storage, and many different things to make it happen. And due to this different type of communication cost, usually it's not the optimal way of sharing like de-identified data from institution to the other institution. And also, besides this, of course, there's this computational challenge, for example, to work on like really large data sets that's collected from different sites. So given this different type of challenges, what we really trying to do is we want to come up with some efficient data sharing strategy that can make this process to simpler, so to make multi-center study to be done in a efficient way. So let's first take a look at what is the current practice for multi-center study. So if you take a look at some recent published papers in the area, like in the medical area or like genomic research, you see that most of the study actually adopts a very similar strategy of using these different data sets. For example, this multi-center data sets will be divided into two parts. And part of them will be used for model development, and the other part will be used for validation. But this validation part is not necessary for all of those studies. And for model development, each of these data set will be used to feed a local model involving a set of parameters. Of course, this parameters, there's a parameter of interest included in this set of parameters. And then depending on the goal, for example, if the goal is to make inference, for example, hypothesis testing on some parameters or get a confidence interval of overall effect size. And what people will do is that they will use meta-analysis to aggregate these local estimates into a overall estimate and then do the subsequent analysis on the joint effects. And if the goal is for prediction, for example, learning, and then these local models basically will be aggregate together using techniques. In computer science, it's called model ensemble. So basically depending on the target population, they will use a validation sample and then to get like a weighted average of the local models. And then the weight will be decided by how each of these local models performs on the target population. So to summarize, the current practice can be considered as a weighted average of local models. And the question that we want to ask is, can we do better than this? Or how and when can we do better than this weighted averaging type of methods? And the other line of research is what I call this distributed algorithm, which is originally motivated from the area of computer science, where they are dealing with the computational challenge working on a huge data set. So what they will do is they will divide the whole data set into subsets and stored in different machines. And then the joint task will also be decomposed into smaller tasks to be done within each machine, and then share some summary level statistics in order to recover these like a target estimates from the joint analysis. And recently there have been a few distributed algorithms developed in the area of distributed statistical inference. And I classify them into two categories. The first category, I call them the lossless algorithms, where the goal is really to obtain the same results as the combined analysis, where the data are all together and ignoring there's data sharing issues and ignore there's computational issues. So this is what I call the lossless algorithms. And for some simple problems like linear regression, because there's a closed form solution, so it can be done, this distributed algorithm can be done by directly decomposing the closed form solution into parts that can be calculated within each of the data set. And for some slightly more challenging problem like logistic regression or other types of problems, because there's no closed form solution and the estimator is often obtained through optimizing an objective function. So there's a group of work, which I call them the distributed Newton methods. So what they do is that they decompose each step of the Newton-Raphson method into smaller components calculated at each institute, and then send back to a central site to get a parameter updates. And then they do this iteratively until the algorithm converge. So this type of iterative algorithm, if it's in a research network that has a sort of infrastructure for this automatic data calculation and sharing infrastructure, which this whole process can be done without human efforts, then that will be an ideal or a very optimal way to do this type of iterative algorithms. But in some of the research networks, because people are not feeling comfortable to, for example, open an API in their databases for this automatically data extraction. So what they do, is that this type of communication is done manually. So statistician will calculate the intermediate results and send to the other sites, for example, by email. So this type of iterative communication can cost a long time, a lot of human efforts involved in this process. So that actually motivates another class of algorithm. I call them the one-shot algorithm, which means that only one round of communication is required to obtain the final results. Of course, meta-analysis is one of these one-shot algorithms, and there's also other types of algorithms developed under this category. So as you can see, for at least for these nonlinear problems, comparing these two types of algorithms, lossless algorithms is more like have more communication costs, but one-shot algorithms usually can only give you approximated results compared to the joint analysis. So you see there's a trade-off between the communication efficiency and estimation accuracy. And our goal is to find a practical balance between these two and provide some solution that is accurate, safe, and fast. So one of our practical consideration that is motivated from our collaboration is that in the research network, we sometimes have access to one of the data set we can call a local data set. Through collaborating with an investigator at this site, we can have access to the local site, but may not be the other sites. So compared to this type of averaging type of methods, such as meta-analysis that only ask for parameter estimates from each of these sites, we wanted to make better use of all the patient level information we have at a local site or say a leading site. And we wanted to borrow information that's in the form of summary level statistics from other sites in order to improve the estimation accuracy. So how can we do that? That's the problem we are trying to answer here. And there's a work developed by Michael Jordan and his colleagues at UC Berkeley, where they developed this approach called the surrogate likelihood approach. Of course, their motivation is more from the computational side. Like I mentioned, you can divide the data set into smaller parts. But they have this nice idea of a surrogate likelihood approach that can be used to answer the question that I just asked. So their idea is like this. So for example, if the data are stored all in one machine, you can construct this combined likelihood function. Suppose we are considering a parametric model. And here I use a simple notation where each site has small n number of samples, and in total there are large k number of sites. Of course, in practice, this all can vary. The sample size can vary. And the estimator from this combined likelihood function is considered as the target or the gold standard. And we want to get a recovered results through a distributed analysis. And in practice, since we can only have access to data from a single local site, suppose it's site 1, we can only construct this local likelihood function using data from site 1. And then the problem is how can we design the information, summary level information to be borrowed from the other sites to make this local likelihood function L1 more like the combined likelihood function in order to recover the gold standard estimator. And their approach is like this. So for a given initial value beta bar, what you can do is you can do a Taylor expansion of the target function, the combined likelihood function. And you see that all of these gradient terms evaluated at the initial value, they can all be distributively calculated because the likelihood function can be is separatable by sites, right? And the problem is that there are so many terms in this expansion. So what they propose is that you can do the same expansion for the local likelihood function. And you can keep the first two terms of the combined likelihood function and then replace all the higher order terms of the combined likelihood function by the corresponding terms of the local likelihood function. Because this local likelihood function, this green box, you do not need any communication to calculate this. And follow this logic, you can write the second equation like this, and then plug in the right-hand side into the red box and drop all the constant terms that do not contribute to the final maximizer. We can get this surrogate likelihood function with a very simple form like this. And the only term that need to be distributively calculated is this first order gradient of the combined likelihood function, which can be decomposed as the summation or the mean of the gradients of local likelihood functions evaluated at the initial value. So this term is a vector of dimensions same as beta. So the communication cost is actually pretty low. And then the final results is obtained by maximizing this surrogate likelihood function. So that's the surrogate likelihood approach. Of course, there is you may already notice that there is a underlying assumption for making this argument work, which is you have to have a local site that the data will be very representative of the total population that you're interested in. Otherwise, this substitution of the higher order terms may introduce error that's not negligible. Okay, so that's the surrogate likelihood approach. And for inference, they show that under regularity conditions, this proposed estimator will have the same asymptotic distribution as a gold standard pooled estimator. And to calculate the calculate the variance for the proposed estimator, because they assume the ID assumption. So they actually suggest that you can do this within the local site. So you can use all your local data to estimate the asymptotic variance, and then you can weight it by properly weighted by the total sample size. So this step, the inference step, will need no extra communications. Okay, so for this surrogate likelihood approach in the multi-center setting, it should work like this. So first step, we have a local site, and then we can calculate the initial value using our local data, and then we can send it to the other sites. And then using this initial value, they can calculate some intermediate result and send back to the local site. And then you can construct the surrogate likelihood function and obtain the final results. Okay, so that's the surrogate likelihood approach. And we extend this surrogate likelihood approach to study the time to event outcome motivated by our collaboration with these research networks. And we consider this algorithm for Cox proportional hazards model. And we encounter some practical challenges. So first is that now the target function is the combined log partial likelihood function, has a form like this. So you see that it cannot be written as a summation of individual terms where each term only involves one data point. So compared to the previous setting, right? So you see the denominator is the summation over risk site, where the risk site is defined as all the sample at risk at a certain time point. Of course, this will involve data from all sites. So the target function is no longer separatable by sites. And the second challenge that we have is because we are dealing with the real EHR data, the distribution of our covariates may vary from site to site. So that will violate the IID assumption from the surrogate likelihood approach. So our ODAC algorithm actually have three main changes compared to the surrogate likelihood approach for addressing the challenges I just mentioned. So the first change is for addressing the non-IID problem. And we find out that instead of asking for the first order gradient from each site, we now ask for the first and the second order gradients of their likelihood function at each site. And after we ask for those informations, our results is consistent even in a setting of the distribution of the covariates is heterogeneous across sites. And the second change is that we are now is for dealing with the non-separatable likelihood issue. So now we, in the initialization step, we ask each site to share the set of event times, the unique event times. So for example, an event happened at site 1, we will ask site 1 to share that event time with all the other sites. And these event time points will be used to construct the intermediate results for constructing the local, the surrogate likelihood functions. That's the second change. And the third change is that in the research network, we find that sometimes multiple sites are willing to serve as the leading site. So the leading site compared to the participating sites will have some extra steps to do, right? So if multiple sites are willing to serve as a local, the leading site, we allow them to do so and to use a common shared intermediate results to construct their own surrogate likelihood function and obtain their surrogate likelihood estimator. And this estimator will be further integrated using a weighted average type of methods. And in this way, we can, our estimator is stable to the way of how you choose the leading site. And of course, for those sites which are not willing to serve as the leading site, they will only be involved in the step of calculating the intermediate results. So that's the ODAC algorithm. And I'm not going to show you the detailed parts of this form of the intermediate results you can find in our recently published paper. And then I wanted to show you some interesting simulation results and our findings. So we did some simulation to compare the ODAC algorithm with the commonly used meta-analysis. So in this figure, you see the y-axis is the bias to the gold standard estimator, which is a Cox regression model fitted on all the data. And each panel here stands for different event rate. So from the left to the right, the event is becoming more and more rare, with the event rate drops from 20% to about 1%. And within each panel, we have 3 different sample size configuration for in total 10,000 data points for 10 sites. And the message here is actually very straightforward. So as the event becoming more and more rare, the performance of meta-analysis is getting worse in terms of both its variation and its bias. So ODAC, on the other hand, can provide a very close estimate to the gold standard estimator and is stable across all situations. So this is the simulation results. And we also apply this ODAC algorithms to a distributed setting where we have 4 claims data sets from Odyssey. And the population of interest is a patient who have a major depressive disorder and who has been treated by at least one of the medication that we're interested. And where the outcome of interest is acute myocardial infarction, considered as a severe adverse event for those medications. And we wanted to fit a Cox regression model with 8 different risk factors. And you can see here some summary characteristics of these 4 different databases. And then this figure shows the results. So each of this panel stands for 1 risk factor, and the 3 methods we're comparing from the left to the right is the gold standard estimator, the meta-analysis, and the ODAC estimator. And we see that across these 8 different risk factors, ODAC is able to provide very close results compared to the pooled analysis, but meta-analysis will have a certain bias across these different risk factors. And for these 4 risk factors, we see that the results regarding whether it is significant, the conclusion is different from pooled analysis and meta-analysis. But ODAC is able to provide a consistent conclusion as the pooled analysis. So far we have already used simulation and real data application to demonstrate the benefit of this type of distributed algorithms. And now I just wanted to talk about these intuitions behind the different methods and why there is a benefit for studying rare events. So remember that the surrogate likelihood approach requires each site to share the gradient of their likelihood function evaluated at an initial value, right? And in a simple case, suppose we have one parameter, the gradient is just the slope of their likelihood functions. And suppose we observe a positive slope at a certain site, that is saying, okay, the final estimator should be to the right of the initial value. And if we observe a negative slope, that is saying that site has information supporting the final estimator to be to the left of the initial value. And all of these slopes will help us to correct the shape of the local likelihood function around this initial value to make it more like the combined likelihood function so that we can get a refined estimator. However, meta-analysis asks for a point estimates and a standard error from each site. And these two information is very sensitive to the rareness of the event. For example, when we are studying rare events, it's likely that some of the sites will only have a very few number of cases or even no cases. Then it's hard to obtain a point estimates and a standard error from those sites with no events. But on the other hand, we can still build a likelihood function and obtain slopes or curvatures from that site, which are not sensitive to the rareness of the event. And by doing that, we do not lose information. We actually integrate all the information from all the sites for the estimation of the population level effects. So that's actually the intuition why there is a benefit for studying rare events using these distributed algorithms. So till now, I think you may already notice that for the ODAC algorithm, as well as the surrogate likelihood approach, what they are considering is more like the situation where you want to do a homogeneous modeling on all the data. So even if the data can be shared all together, can be saved in one machine, you still want to fit the same model on all the data that you have. Well, in practice, sometimes you may not feel very comfortable to do that because there could be set specific effects that you wanted to account for in your modeling approach. So for heterogeneous modeling, there could be some choices like how you do this type of heterogeneous modeling. For example, we can consider like fixed effects model. Fixed effects model means that we can assume part of our parameter to be common parameters to be shared across sites. But the other parts of the parameter could be set specific, so they could be very different. For example, in a regression, you could assume that the treatment effects is shared across all sites, but the effect sizes of other confounding factors could be very different across sites. And that's one possibility. And also you can use, if you have extra information on this nuisance parts, you can assume they follow this random effects model. So this different parameter will from each site will follow a normal distribution, like a higher level distribution with a parameter beta here. So that's random effects model. And if you're not comfortable to make any of these assumptions, we can also consider like more data-driven approaches to avoid specification of which part of your model may likely to be the same or not. I will go back to this different modeling approaches later. But as you can see, for any of these heterogeneous modeling approaches, the surrogate likelihood approach will no longer apply, because the key step of this local approximation of the combined likelihood function will cause problem because of the heterogeneity. So for the fixed effects model, so which is like the part of the parameter is common and the other parts can be different. For this setting, we have a work that extends the surrogate likelihood approach to handle this fixed effects modeling problem, and we have several considerations. So in that setting, the first consideration is a technical consideration where we want to change the target function from the combined likelihood function to the combined efficiency score function. And in this way, so the efficiency score function is a projection of the score function for beta projected onto the space that is orthogonal to the score function for gamma. In this way, we kind of decorrelate this parameter beta and gamma, and that we can reduce the impact of some plugin estimator gamma on the estimation of the parameter of interest, which is beta. So this is a technical step. And after we change this target function, we have a second consideration, which is we want to do the same thing as the surrogate likelihood approach, which is to do a higher order matching of the gradient terms. So we want to find some function g where the higher order gradients of the function g can match the function, the gradients of the target function. And I read this goal as the form of taking expectation. And you notice that since we want to do a local matching, the first expectation is with respect to the distribution at our local site, F1. But the second expectation is taken with respect to the data distribution at each site. So this seems to be a very difficult task, but that can be solved by a simple technique called density ratio tuning, which means for some function S, if you multiply it by the ratio of these two densities, Fj over F1, and then you take expectation with respect of F1, you get the same thing as if you take expectation of function S with respect to Fj. So because of this, we can define function g having this form here, where the right term is for the density ratio parts. And then we can do the same higher order matching. So the surrogate efficient score function will have this form here, where the right term need to be distributively calculated, and the green term is for a local matching. And the final estimator can be obtained by solving this estimating equation. And for construction of this surrogate efficient score function, each site need to provide initial estimates for gamma j and also some intermediate results, which has this form here, function sj, that is a vector of dimension same as beta. So the communication cost is similar as the surrogate likelihood approach. Okay, that's the idea of our method. And this algorithm is slightly more complicated compared to the surrogate likelihood approach. So now the first step is that we ask each site to calculate some initial value for their own parameter values, and then they will pass this parameter estimates to the local site. And since beta is assumed to be a common parameter, we can further aggregate it and send back to a local site through a weighted approach. And then with this beta bar and initial value for each gamma j, each site can calculate the intermediate results function s and send to the local site. And then we can obtain our final results through construction of the surrogate efficient score function. So in practice, of course, we wanted to avoid iterative communication. But in theory, we're really interested in if further iteration can help us improve the results. So basically for iteration, you can send back this results of beta to each site and use that, they can update their value for function S and then do another round of parameter updating. So that's how you can do iteration. And then we first did a theoretical investigation on some desired properties of our proposed estimator in terms of consistency, rate of convergence, and also distance to the gold standard estimator, asymptotic normality, and efficiency. And so we have some theoretical results. I'm going to skip all these theorems and go directly to the conclusion. So for the conclusion part, our estimator is proven to be better than meta-analysis in terms of the distance to the gold standard estimator. So if you don't do iteration, that means t equals to 1 here. The distance is already closer to the gold standard estimator compared to meta-analysis. And one extra round of iteration will further reduce this distance. And another benefit is about asymptotic efficiency. We show that our estimator, no matter how many iterations you have, it's asymptotic efficient in terms that the variance reaches the Cramer-Raw lower bound. But meta-analysis will not necessarily be efficient. And we also did some simulation results and real data application using data from the One Florida clinical research network. But the conclusion is very consistent with this theoretical, our theoretical findings. So I'm not going to show you here, but you can find more detailed results in our recently published paper. So that's for fixed effects model. And we also did some work regarding the random effects modeling approach. So for the random effects model, allowing random effects, we start with considering continuous outcome and consider the linear mixed model setting. And due to the simplicity of linear regression, we actually, the proposed algorithm has some nice properties. So we're able to show that within only one within only one round of communication, we can achieve lossless recovery of the results as if the data are pulled together. So it's both lossless and one shot. So that is due to the special property of linear model. But we are now working on the generalized linear model settings, and that's apparently more challenging than this linear model problem. We're currently working on that. And finally, I want to just to briefly talk about this data-driven approaches, because I think this is more practical, as in some of the situation we're not able to assume, or we're not comfortable to assume any of the similarity structures between parameters across different sites. And for data-driven approaches, now we are considering the setting where, for example, each data set will have their own set of parameters, beta j, and we don't know, like comparing the first site to another site, for example, site j, we don't know how close these two parameters are, and we don't know in what way they are close. For example, if these two regression parameters, they are all, they share most of their coordinates, then this distance beta 1 minus beta j will be a sparse vector. So if you quantify the distance through a L0 norm, then the difference may be very small. Or they could be like nearly sparse. So for example, each coordinates of these parameters between these two sites can be very small, and then there is aggregated effects. If you take, for example, a L2 norm, they can be small. And this classification, this characterization of this difference, I can use some type of norm, and then that's bounded by a constant h. but I'm not going to specify in which norm they are small and how small are they. So H and Q are totally data driven. So we are developing a type of method that can provide a robust, adaptive integration of data. So ideally, if H is very small, then we can borrow more information from the J side to the target side. But if this H is large, we want to automatically account for this huge heterogeneity between two data sets. So that's an ongoing work, and I'm very much expecting to share with you more after we get some more concrete results from data analysis. Okay, so I will stop here, and in summary, what I wanted to show you today is that in this research network, because a lot of efforts has already been done to provide us this great resources and platforms for multi-center study, and we as the statisticians, we want to develop some more efficient data sharing strategies that are able to extract common knowledge contained in these heterogeneous data sets. And this, of course, will need us to collaborate with domain experts and informaticians to know better about the data. But I mean, through well-designed algorithms, we are definitely able to do better than some naive approaches like averaging type of methods. So that's our conclusion, and I will stop here, and I look forward to your questions and also future collaborations. Okay.
Thank you so much. That was very exciting and interesting. We have one question from the audience. So Michael Brody is asking, so in the first part of your talk, prior to heterogeneous models, do you assume that the data in each distributed site is identical, i.e. based on the same analytical model, features represented by the data?
Right, so for the homogeneous modeling, we need the same features to be extracted from each of the data set. And also it requires the model or the conditional model to be the same across all data sets. But as I mentioned, for the ODAC algorithm, the feature distribution can be different.
I see. Thank you. And I also have sort of a related question. So, and you know, just for the sake of the argument, I agree that why use meta-analysis when you have now this method that doesn't produce bias. But I was wondering, so the different features that you were showing on the plots, they had like different amount of bias. And is there any way, some diagnostic tools to sort of know upfront how much will you be in trouble if you decide to use meta-analysis?
That's a really good question. I think it's hard. So suppose our goal is actually depending on our goal, right? So if your goal is for prediction, so you wanted to train a prediction model, and that's good in the overall population, at least we have some way to validate whether the performance of each type of methods. You can just use a set of data to test the performance of the prediction accuracy. But if it's on the other domain, for example, causal inference or association, right? So because we don't know the truth, it's hard. It's normally hard for us to detect whether what is a bias for meta-analysis. But I think if you have a better understanding of the data, so you can do like you can fit local models and you can compare. So in meta-analysis, there's a way of quantifying this heterogeneity across different sites. So that heterogeneity can be one sign of whether meta-analysis is reliable. If the level of heterogeneity is really big, then the assumption, if you use a random effects model in meta-analysis, that's basically assuming the data, the different sites with the data are exchangeable, right? So that definitely violates this type of assumption. So you have this sign of the heterogeneity is too large, so you cannot trust very much on the meta-analysis part. So I think like model diagnosis, you're right about that. So meta-analysis, they have a way of quantifying this level of heterogeneity. And also you can develop sort of a test compared to different data sets if you have some parameter of interest to see whether they are the same. But I always have this doubt on developing a testing mechanism to figure it out, as we have a lot of samples, and of course there's no identical distribution of the data in practice. So normally I guess the test will be easily rejected. But I'm hoping that we can develop some model diagnosis tools to really test to figure out which approach has a better performance.
Yeah, that's, it's always fun to take a look at the data, right. So that'll be fantastic.
Yeah.
So I actually had a question in the opposite direction. So thinking about why wouldn't you do a pooled analysis? So why wouldn't you take the effort to get the data from all the individual sites? And how would you know? Because I think so that data set construction and being able to I think there's like administrative things about, how can you do data sharing agreements, but then there's also de-identifying the data and things like that before you then get the site. So there's effort on that side if you want to do a pooled analysis, but then you have all the data and you can look at more of these questions. But on the other side, I think there's, with the distributed algorithms, I think there probably is some computational, computational and administrative costs to getting that distributed algorithm implemented at each of these individual sites. So how do you weigh those two when you're making the decision?
And that's a great question. So for me, I think a more important problem, as you can see from my talk, is to consider if the data are actually, you can get access to all the data, or we can manage the some type of administration efforts to get all the de-identified data together. We still get the question of how to correctly model them, or how do we understand this heterogeneity, right? So if we can come up with a modeling approach first, in the case where data are all stored together, that's like we already finished one step. And then it's a problem of whether this network is more suitable for doing this de-identified data pooling mechanism, or if it's more suitable for doing a distributed analysis. If there's collaborators at each side, a statistician at each side are willing to do the intermediate computation, intermediate results to compute and then to send to the share to the other sites. So in different research network, I would argue that this difficulty is different in different level. And after we figure out how you do the analysis when the data are stored together, there's techniques in both like computational side and in statistical side that we can develop to manage. You can get a still approximated results for the pooled analysis. And if the network do not have the problem of sharing data, of course, we'll just use the pooled analysis to get a result. And if it's really too hard for them to do this pooled analysis, we can use a distributed algorithm to get approximated but also accurate results. That's what I understand.
My guess will be that sort of get IT folks together to implement some of the actual networking of the identified data will be easier than to wait like for 2 years while the administrative stuff goes through. In situations like COVID, that might be too late.
Yeah.
This is very interesting because I guess more and more these days that will be a more essential problem with the data sharing, and especially in a situation when we need to include more and more diverse populations in our research, and different, like with Harvard cohorts, we don't really have much of the access to the diverse populations. So to make our findings to be generalizable, it will be wonderful to have a nice and easy way to engage other collaborators where they, don't need to share all their data or like give access to their data indefinitely.
Yeah, I agree.
And I think some of the factors that are considered identifiable information, like that you can't share, but could be actually quite an interesting like aspect of the research to study, like this would be the way you could actually look at those, you couldn't share.
Right.
Yeah. And specifically like missing covariates and having different sets of covariates, that's critical because nobody has the same covariate.
Right, that's true. So we actually have considered that. So each site can have different set of covariates, but relies on some assumptions we can also do this information borrowing from different sites, even their features are different.
Yeah, I think that's absolutely critical. Well, I guess we don't have any more questions. So thank you so much. It was very exciting and very interesting.
Well, thank you.
Thank
you for inviting.
Yeah, whenever you get updates, let us know. We'll be happy to have you again.
Okay.
Hopefully our next time you visit us, it'll be in person.
Yeah, that will be very good if we can meet in person.
Yeah.
Yeah.
Absolutely. Well, thank you everybody for joining.